Hi, everybody. Thank you for joining our webinar today. Just a couple of things to keep in mind. This webinar is being recorded, and we will distribute the recording and the slides by the end of the week. Just another note that our website will be updated sometime this week, early next week, with our calendar of webinars for the rest of the year. So feel free to go ahead and register for those. But as long as you're on our email list, you'll see those come through. With that, I will pass it on to our first presenter.
Great, thank you, Kate. Good afternoon, everyone. My name is Anushka Cholika. Thank you for joining us today. We're excited. This is going to be a special webinar on the Ultra Low NOx Boiler Burner Project, which was completed under the California Statewide Gas Emerging Technologies Program. The program is implemented by ICF and administered by SoCalGas. Just a quick background, this project was launched back in 2023 and was completed last year. If you're joining us here for the first time, for those who may not be familiar with the Gas Emerging Technologies Program, also known as GET, essentially the program is a collaborative effort among the state's major gas utilities. Its mission is to identify, assess, and accelerate the adoption of promising new emerging technologies that can help improve energy efficiency, reduce greenhouse gas emissions, and support California's ambitious climate goals. And this program helps play a vital role in bridging the gap between research and real-world application. So for today's session, we will focus on an emerging boiler burner technology that can significantly reduce nitrogen oxide emissions while also operating at greater efficiencies than typical burners. So for the agenda today, we'll kick it off with an introduction on the project team, followed by the project objectives, and then we'll have ClearSign go into the testing and the results, followed by the conclusion recommendation. So this is just a brief overview on the project team. We have myself and Stephen Long from ICF. On the right, we have Venki Iyer from ClearSign and Troy Edens. They completed the technology assessment and are the overall technical lead for this project. We also had a third-party engineer, Dean Jansen, provide testing oversight and data validation. So without further ado, I will pass it over to our technical lead, Venki from ClearSign, to take it from here.
Thanks, Anushka. I want to thank ICF for this opportunity to present the work, and I also want to thank them for their support throughout the duration of the project. I want to acknowledge SoCalGas, Southern California Gas, was the administrator for the California Statewide Gas Emerging Technologies Program. I want to thank California Boiler for allowing us to set up the test boiler and all our measurement equipment in their backyard. And then, like Anushka said, Dean Jansen, a professional engineer who provided independent oversight and verification throughout the setup, testing, analysis, and reporting phases. So the project is part of the California Statewide GET program, which focuses on identifying and evaluating commercially available emerging technologies and enabling their adoption. And the emerging technology in this project is the Rogue ClearSign NZN burner, which is NZN stands for Near Zero NOx burner. Its efficiency and performance and emissions were compared to an industry standard baseline. The industry standard baseline was picked for this project was a mesh style burner, which uses a metallic fiber mesh to surface stabilize a premix flame and is capable of achieving sub 9 ppm NOx. The Rogue ClearSign burner, as the name suggests, is capable of achieving near zero NOx level or less than 2.5 ppm NOx. But for the sake of the project, we decided to add another phase of testing at comparable NOx levels to the baseline. So there are two phases of the project. The first phase was the baseline tested at sub 9 ppm level. In phase 2, we did a phase 2A where the Rogue ClearSign burner was detuned to operate at sub 9 ppm, and then it was tuned to operate at its lowest possible emissions level of sub 2.5 ppm NOx. The metrics that were studied here or measured were NOx emissions, carbon monoxide emissions, boiler efficiency, the fuel gas usage, and the electrical energy usage. Next slide, please, Anushka. So this is some photographs of the two burners. In the background, you see the boiler that was the test boiler for this project. On the left, an industry standard ultra low NOx mesh burner is installed onto the boiler. Again, like I said, it uses a metallic fiber mesh to surface stabilize a premixed flame, and then the premixing and dilution with excess O2 is what enables its low NOx operation. On the right is the emerging technology of the Rogue NZN burner powered by the ClearSign core technology. If you'd like to learn more about the burner itself and how it achieves the low NOx, I would encourage you to visit the ClearSign website and the Rogue combustion website. That'll talk about details of the operation and our approach to getting the extremely low NOx emissions. There are no catalysts or chemicals used to achieve the low NOx. There's no external flue gas recirculation. The burner reduces the NOx emission right at the combustion point and right at the source. Next slide, please, Anushka. Well, look at the test setup and approach here. So in the middle, there is a Cleaver Brooks CB700 125 horsepower boiler. And then the boiler system had a feed water tank and a steam vent and condensate tank. There was no, the steam was not captured, or the condensate was not recycled back into the boiler. So steam was just vented into the atmosphere, and 100% makeup water was used to replenish the water back into the boiler. In this photo, it shows the ClearSign Rogue burner installed, but in the prior phase, the baseline burner was installed here. Next slide. So we'll talk a little bit about the test approach and sort of the basis for the measurement and the protocols that we used. The testing was based on IPMVP guidelines, which is an international protocol for measurement and performance verification. So as part of this protocol, what's done is that you isolate the boiler burner system and its energy use from the rest of the facility, so you can really test the system by itself without worrying about the consumptions of any other equipment that's part of the facility. So it's like drawing a control volume or a control box around the boiler and burner system and measuring all the flows and all the energy input and output going in and coming out of the boiler system. So that included measuring with the water flow, the pump pressure, the temperature of the feed water going into the boiler, the fuel gas flow going in, the pressure and the temperature of the fuel gas going in, the combustion air flow going in, the temperature, relative humidity of the air, the combustion products going out of the boiler, and then the steam produced, the flow rate of the steam, the pressure, and the temperature of the steam. In addition, the electrical energy usage were also measured for the control system, for the VFD, the pumps, and the blowers, and so on. So it's like measuring all the energy input and output of the boiler burner system for each phase of the project. Next slide, please. So the the firing rate of the burners for both the baseline and the Rogue ClearSign burner was 5 million BTUs an hour. That's the design heat release rate. We had picked a few different test conditions, 25% firing rate, which corresponds to a 4-to-1 turn down, a 33%, which is about 3-to-1 turn down, a mid-range firing rate of 66%. And we wanted to do 100% on the baseline burner, but the blower was limited and we could only fire up to 84% of the rated firing rate. And there are a couple of reasons for this. One was that the mesh style burner that we used, the baseline burner, it was refurbished. So I think that there might have been some blockage on the blower inlet filter and the mesh, which created additional pressure drop and limited the blower capacity. And then the other thing is that in order for the baseline burner to operate at sub 9 ppm levels, we had operated at pretty high levels of excess air, and that also used up some of the capacity of the blower. So I think for a higher NOx limit, we could have gotten up to 100%, but since we were trying to measure to its lowest NOx capability, we were limited on the firing rate of 84%. On the Rogue ClearSign burner, we repeated all these test conditions of 25, 33, 66, and 84. But in addition, we were also able to test the 100% firing rate condition. So we'll present data on all these operating points and then the additional 100% point, which will not have a basis for comparison on the baseline. We'll still look at the data for that condition. The NOx levels, like I talked about before, will be sub 9 ppm for the baseline burner, and then for the Rogue ClearSign burner, we'll test it at the detuned 9 ppm and then the tuned sub 2.5 ppm. So it's two different conditions for the Rogue ClearSign burner. Next slide, please. So a couple of photographs to show you what the flame looks like. So on the left is the mesh style burner. So it has a long metallic mesh insert that goes inside the fire tube. And then the glow that you see like a halo around the central cylindrical portion, that's the surface stabilized premixed flame. And the light blue appearance, that's typical of what you would see in a premixed flame. On the right is the Rogue ClearSign NZN burner. It does not have a mesh element. It uses a swirler to stabilize the flame. And again, there's a metallic insert that goes into the fire tube, and then there's a swirler at the end of the burner insert, and that's where the flame is located. So this light blue circle that you see in the middle, that's the swirler flame, and then the main flame is kind of anchors around that central swirler flame. So just to give you an idea of what the two flames look like. Next slide. So we'll look at the efficiency numbers in a moment, but I just wanted to show you the steam generated from the two boilers and how it correlated to the amount of fuel flow going into the to each burner. So there's 3 sets of data points: the dark blue circles, the light blue circles, and the red triangles. The red triangles are the baseline mesh style burner, the industry standard burner, and the light blue and the dark blue circles are the ClearSign Rogue burner. And there's 2 modes. One is the S9 mode, which is a sub 9 ppm mode, and then the NZN mode, which is a sub 2.5 ppm NOx mode. So 3 sets of data points, and you have 5 different firing rate conditions: 25%, 33, 66, 84, and 100. Steam flow on the y-axis in pounds per hour, and then the fuel flow in standard cubic feet an hour on the x-axis. So as you can see, that at the low firing rates, there's not much of a separation between all the data sets, but when you go to the 66, 84, and 100, it's clear that the ClearSign Rogue Burner generated more steam flow for a given fuel flow than the baseline mesh burner. So the rates of steam produced were higher compared to the baseline. On the next slide, we'll see how that translated to an efficiency number. So when we talk about the boiler operating efficiency, what that is it's comparing the heat transferred from the combustion process into the water, and in order to heat up the water up to its boiling point and then convert it into steam. So that's if you look at the equation on the right, that's the Q dot out, that's the output heat, and the Q dot in is the energy that's going into the combustion process. So that's the chemical energy stored in the fuel and released from the combustion of the fuel and its conversion into carbon dioxide and water vapor. So that's what we're doing to calculate the thermal efficiency. I've tried to keep the same color combination for the different data sets. Red is always going to be the baseline mesh data points, and then the dark blue is going to be the ClearSign Rogue Burner at sub 9, and the light blue is going to be ClearSign Rogue Burner at the sub 2.5 or NZN NOx level. So on this chart, you have boiler operating efficiency on the y-axis and the burner firing rate on the x-axis. And there's a 25%, 33%, 66, 84, and 100%. And you can see that the highest thermal efficiency was for the Rogue ClearSign burner operating at 9 ppm levels. Next was the ClearSign Rogue burner operating at the NZN levels, and the lowest efficiency was for the baseline mesh burner. From an overall standpoint, this range of 75 to 80, 81% efficiency is pretty typical for these size of boilers. So that's consistent. And then the reason that the efficiency is lower as the firing rate goes up is because the heat losses from the system also go up the higher at the higher rates of operation. So that's why all these three curves have a downward trend as the burner firing rate goes up. So what's the cause of the efficiency difference between the baseline burner and the ClearSign Rogue burners? And we'll learn about that on the next slide here. So the primary difference that causes this difference in operating efficiency is that these burners operate at different levels of stack O2 or oxygen content in the exhaust, or another term that the industry uses is the amount of excess air that's introduced into the combustion process. Now, both the burners use a premixed flame system, and a characteristic feature of premixed flames is that the higher excess air that you introduce into the combustion process, the lower the flame temperature is, and the lower the flame temperature is, the lower NOx that is generated in the combustion process. So it's one of the approaches that a lot of ultra low NOx burners take is to operate at elevated levels of excess O2 or excess air in order to reduce the NOx emissions. Now, the downside of such an approach is the downside is that you're adding all this excess air that then takes up heat away from the combustion process, and there's less heat available to transfer to your process or heating up water or making steam. So there's a loss of efficiency associated with operating at higher and higher excess O2. So getting back to this chart, the baseline mesh burner operated at around 8% O2 in the stack. The ClearSign Rogue burner operating at 2.5 ppm had about 7% excess O2. And when the ClearSign burner was detuned to operate only at 9 ppm, it could operate at a much lower O2. And around 4 or 5% O2, and that's what resulted in its then in the S9 burner getting the highest efficiency, and then the baseline mesh burner getting seeing the lowest efficiency. So you kind of see a downward trend in efficiency the higher the stack O2 or the excess air that is used for the combustion process. So that's sort of the main underlying reason for the difference in efficiency or the efficiency gains for the ClearSign rogue burner. The next slide, please. So this is just looking at the same data, but plotting it as a function of the NOx emissions. So here on the y-axis, you have the boiler operating efficiency. On the x-axis, you have the NOx emissions. So the baseline mesh burner operated at sub 9 ppm. So you see a whole range of NOx emissions depending on what firing rate we were at, from 6 to 8 ppm. We kind of added just another ppm of padding so that we didn't deviate from the sub 9 requirement. Same thing for the ClearSign Rogue S9 mode. We try to operate around 6 or 7 ppm. And then you kind of see that the group of red points sits below the group of the dark blue points, which shows an efficiency gain for the ClearSign burner at S9. And then the light blue points was when the ClearSign burner was tuned for its lowest possible NOx. You see all these points are below 2.5 ppm NOx levels, and it takes a slight efficiency hit compared to the baseline burner, but it still provides a gain compared to the baseline mesh burner. So the Rogue ClearSign burner provided higher efficiency and also lower, much lower NOx. And these NOx numbers of less than 2.5 are comparable to SCR systems or selective catalytic reduction systems that use a post-treatment process with chemicals to reduce the NOx after they've been formed, whereas the ClearSign burner reduces the NOx right at the source. Next slide, please. So this is just looking at the efficiency, but in a different way in terms of stack energy losses. So the heat, part of the heat that's generated in the combustion process gets transferred to the water and the steam. There's more heat that's lost to the environment, and then finally there's a third portion of the heat that just goes out in the combustion products. Because the combustion products exit the boiler at a high temperature, so there's some energy loss associated with those combustion products. And this plot shows the stack losses plotted against firing rate, and you see that the lowest stack energy losses were for the Rogue ClearSign burner operating at the S9 conditions. Next slide, please. So this slide compares the fuel energy used for the different test cases. Again, the red symbols are the baseline mesh burners, and the blue circles are the ClearSign Core for the S9 and the NZN modes. The fuel energy usage was normalized here just so that we can compare apples to apples case. So it's normalized on a per pound of steam produced basis. So the unit on the y-axis is a BTU per pound of steam produced. On the x-axis is the burner firing rate. Again, as you can see, the amount of fuel energy used is highest for the baseline mesh burner and lowest for the ClearSign Rogue burner at S9, and then the ClearSign Rogue burner at NZN levels fall right in between the other two data sets. So the Rogue ClearSign burner provided a savings in fuel energy use. That's the takeaway. Now we've looked at fuel energy consumption. Now on the next few slides we'll look at the electrical energy use, and there's a few different components of the system that use electrical energy. The first being the feed water pump, and it's a pretty tight grouping for all the different cases because of the amount of feed water getting pumped into the boiler. It did change a little bit depending on the steam output, but it did not affect the energy consumption of the pump in any significant way. So that's why all these points are kind of grouped together pretty tightly. And then the pumps tend to get more efficient the closer they are to their design condition, which is why you see that the energy consumption goes down as the firing rate goes up. So it's just the pump operating more efficiently. Next slide. So now we'll look at the blower electrical use. So there's quite a difference between the red, how the red points are trending and the blue points are trending. And the reason for that is that the baseline mesh burner used a fixed speed blower, and the way it regulated the amount of airflow for the combustion process at different firing rates was by opening and closing a combustion air damper. So it being a fixed speed blower, the blower got more efficient as it operated closer to its design rate, which is why the electrical energy use actually went down at the higher burner rates. Now, the ClearSign Rogue burner used a VFD or variable frequency device or variable speed device, which allowed the blower or the blower motor to operate at different speeds. And what that did is it allows the blower to operate more efficiently, even at the lower firing rates, and reduce the electrical energy consumption. So at the 30, 25, and 33%, the ClearSign Rogue burner blower would run at a lower speed, and then it would ramp up as needed at a higher firing rate. So it allowed the blower to operate more efficiently, and then but despite that, since the amount of excess air that was used for the ClearSign burner was lower than the baseline burner, it showed a lower blower electrical usage even at the higher firing rates for the ClearSign Rogue burner. And then since the ClearSign Rogue burner used a little bit of higher excess air for the sub 2.5 ppm, those points kind of fall in between the ClearSign S9 and the baseline. So it kind of explains the differences in electrical energy use between these cases. Next slide. So now this is combining all the electrical energy use, the energy used by the pump, the blower, the control panel, and all that grouped together. So this is the total electrical energy used by the entire boiler burner system. The red points again show the highest electrical energy use, and it shows a downward trend at the higher firing rate. So this is primarily, the differences are primarily driven by the blower energy use, and then you see that the ClearSign Rogue NZN and S9 electrical energy use is lower than the baseline, and that's because of lower excess air operation and the use of a variable frequency device on the blower. Next slide. So this is sort of a summary slide looking at all the fuel and energy savings for at least two of the firing rate cases. We've picked the 66% and the 84% here. So we'll go one column at a time. So the fuel energy per pound of steam produced, the baseline mesh burner had about 1392 BTUs per pound, and then the ClearSign Rogue NZN at 1339 BTUs per pound of steam produced. The ClearSign Rogue S9 at 1317. So when you do a percentage basis, when you do the comparison, the ClearSign Rogue S9 showed a 5.4% reduction in fuel use, and the ClearSign Rogue operating at sub 2.5% showed a 2.5 ppm NOx showed 3.8% savings in fuel use compared to baseline. And when you go to the higher firing rate, the savings were 4.7% for the S9 mode and 3.3% for the NZN mode. When you look at the electrical energy use per pound of steam, again, the S9 burner showed 33% savings in electrical energy use compared to baseline. And then the ClearSign Rogue NZN showed 25% savings in the baseline. And then at the higher firing rate of 84%, the savings were 25% electrical energy use savings, and then 7% savings in the NZN mode. Next slide. So this is a photo of what the ClearSign Rogue NZN burner looks like. So on the left-hand side end of the burner is where the flame is stabilized, and on the right-hand side, the big circular plate is what is a connection plate to the boiler. This screen shows a control panel provided by Rogue Combustion, and it shows all the operating conditions, the valve positions, the operating O2, and the blower operating condition, and blowers and steam output and all that. So the advantage of the ClearSign Rogue burner over the baseline is that not only do we get an unmatched level of NOx performance of sub 2.5 ppm level, since the ClearSign burners operate at a lower excess air, lower operating O2 compared to the baseline industry standard burners, there's also an efficiency gain and reduction in fuel energy use. So that's sort of the biggest takeaway. Next slide. So just to conclude, the ClearSign Rogue burner demonstrated higher operating efficiency, fuel savings, and electricity savings, not only at the comparable NOx levels of sub 9 ppm, but also at the lowest possible NOx emission levels of sub 2.5 ppm, which is comparable to even post-treatment NOx reduction techniques like SCRs. So, yep, next slide, please. So in terms of recommendations, how do ClearSign and Rogue plan to use the study to support our commercialization efforts? So the quantification of fuel and energy savings kind of provides us with a basis to do a techno-economic analysis for existing boiler operators. So we can go to a customer and offer at no cost to them a techno-economic analysis for how much fuel and energy savings they could see on an annual basis compared to their existing burner if they were to retrofit the ClearSign Rogue burner. So not only would they be able to meet the extremely stringent NOx regulations in the South Coast or San Joaquin Valley air districts, but at the same time also benefit from fuel savings and electricity saving costs, which would then allow for pretty much the burner kind of to pay itself back over a reasonable amount of time. So the study was very helpful for us, and we're very thankful to SoCalGas and ICF for the support. Also, we're trying to work with SoCalGas and ICF for a next phase of this project where we're looking to offset about 30% of the natural gas in the fuel, or natural gas in the fuel with hydrogen, and this will allow for consumers to not only reduce their NOx emissions and realize fuel savings, but also reduce their CO2 emissions because you're offsetting the carbon from natural gas with hydrogen fuel. So we're trying to set up a next phase study to test the ClearSign Rogue burners with up to 30% hydrogen initially, and then expand that to 100% hydrogen fuel. So stay tuned for news on those projects. With that, I do want to thank ICF and California Boiler again for their support. I want to thank my partner in crime, Troy Edens, for his help and support throughout the project, right from setup all the way through the reporting. And thanks again to Anushka for her support. That's all, and I'd be happy to answer any questions.
Thank you, Venki. That was a great presentation. I think I see a couple of questions in the chat. So Alfredo asked what fuel was used for the test, and did you modify the burners in order to shorten the flame?
So what fuel was used for the test? Yeah, so the fuel used for the test was natural gas. So just just from the city utility line, so low pressure natural gas. And then we did not modify the burners in any way. A feature of using premixed combustion is that the flames tend to be quite compact themselves, and the reason for that is that in a non-premixed flame, you have to rely on a natural diffusion for the air and fuel to get into the flame zone and completely combust. But for a premixed flame, you've already kind of allowed the air and fuel to come in intimate contact, and that allows for the combustion process to not take up as much area, and so the flames tend to be more compact. So just by the design, just by the inherent design of premix burners tend to have a compact flame. So no, we did not need to modify the burner specifically for this study. It's a feature of our burners.
Thanks, Venki. There's another question from Adam Spitz. He asked, are there subjective studies on performance? Everyone has a different opinion on comfort.
Subjective studies on performance. Not quite sure I understand the question. So from an emissions point of view, the ClearSign Rogue burners have been already installed in 5 or 6 applications, and they've been independently source tested at sub 2.5 ppm levels, NOx levels. So it's been the performance has been independently verified. Our burner technology for other applications, process heaters, have been recognized as best available control technology by the South Coast Air Control District in the LA area, SCA QMD, at least for a couple of applications. But I think this was one of the first efficiency studies that was carried out to characterize the sort of the thermal performance for these burner technologies and for boiler applications. So I think it's sort of one of the first of its kind studies from an efficiency point of view, but the emissions has been widely tested out even prior to this project. I see another question. If I want to use this burner with heated air, what is the maximum rated temperature? So the technology, the ClearSign Rogue burner, can be applied to air preheat systems. We have looked at air preheat applications for process burners. We've not really come across an application requirement for a boiler burner, but we can definitely evaluate it. On the process burner side, I think we could probably do 300 to 400 degree Fahrenheit for air preheat. We'll have to take a look at the actual application, the process, the size of the heater, in order to kind of estimate performance and NOx emissions. So we'll really need to know what application it's going into. If you have something in mind, Mehdi, then I would encourage you to reach out to us so that we can understand your application and see what we can do. How much energy does a blower use for premixing air and fuel? It's a great question. I'm trying to think about the horsepower levels. So in order to get good premixing, the blowers have to run at a high, elevated pressure. So typically the blowers run around 8 to 15 inches of water column. It was quite comparable for the baseline burner as well as the ClearSign burner. If for the NZN mode, the ClearSign burners operate at a higher discharge pressure and hence a higher horsepower use. I think for this size burner, the typical blower horsepowers would be around 5 to 8 or 9 horsepower. So, and I think that's pretty similar for both the Rogue and the baseline, about 5 to 9 horsepower.
I don't see any more questions. Does anyone else have a question for Venki?
Also, if anyone wants to come off mute, please just raise your hand and I can unmute you if you prefer to ask your question live.
While we're waiting for any questions to come in, this is our sister program, CalNext, which focuses on emerging electric technologies. If you're interested in this program, you can go to calnext.com for more information. And if anyone has any questions on ICF or the GET program, feel free to reach out to us. Here's a contact for our program. Our program manager is Ava Donald. You can also follow us on LinkedIn. And if there are no other questions, I'd like to thank Venki once again for presenting today and for going over this project, and for the ClearSign team and Cal Boiler and Rogue Combustion team for their participation in this study.
Thank you. Thank you for the opportunity, and thanks to all the attendees for your time.
Yeah, thank you everyone for attending. All right.
Thanks, everyone.
Thank you.
Thank you all.